Hello. In this talk, I'm going to talk about multi-fidelity Bayesian optimization for Syngas Fermentation Simulators. I'm Mahdi Eskandari, PhD from University of Kent in machine learning for wireless communications and also from Matterhorn Studio. The overview of what I'm going to talk about today is about multi-fidelity Bayesian optimization. The Bayesian optimization is an advanced technique for optimizing the complex and expensive to evaluate functions, typically maximizing or minimizing functions when multiple source of information or fidelity is available. Traditional Bayesian optimization scenarios focus on just single fidelity or just one information source that is even very complex or very expensive to evaluate. But multi-fidelity Bayesian optimization, we have access to multiple source of information that is some cheaper information that is not very exact or some expensive evaluations that are precisely true or accurate. In order to understanding further about MFBO, the basic principle at its core is MFBO combines information from multiple fidelity levels in order to construct a surrogate model for the target function, okay? And the low fidelity models or the less accurate models provide some approximation of the target function that are faster and cheaper to evaluate. And the high fidelity models are the models that the very exact, very accurate, and also computationally very expensive, but it provides us the exact output from the input, not the approximation or estimation of the very exact one, even if it is very expensive. And surrogate model is a Gaussian process or somehow some other random processes that in order to model the black box function that we are going to optimize. I'm going to further discuss more about one by one of these functions. The Bayesian optimization in a very simple form as its framework goes like this. At the very first step, we have a number of data that are initially available. So it is our starting point. So we fit a Gaussian process to those points that we currently have, and based on a acquisition function that could be probability of improvement or expected of improvement, we choose the next point that we are going to evaluate. So we find that point and evaluate that point and find a result and update the surrogate model based on that and go through this process until the budget is exhausted or how many iterations we are going to have. There are some key challenges here. One of them is the cost of using each information source, because as I said, the high fidelity one is very expensive, whereas the low fidelity one is very cheap. So the cost of these two would be different. So the problem or a challenge could be in the case that the ratio between these two costs are very high or very low. So this is a challenge that I'm going to discuss about this further. There are some real-world applications of multi-fidelity Bayesian optimization or even Bayesian optimization that are in the engineering design or hyperparameter tuning of machine learning, or in aerospace or aircraft designing, and many more. But in our problem, the specific use case of MFBO that we are going to explore more is MFBO for Syngas Fermentation Simulators. A Syngas fermentation is a technology that, in a very, very simple form, it takes some variables as input in a specific environment in terms of pressure or temperature, and gives some gas as output in a simple form. So this process is very expensive, very costly, and also very time consuming in terms of time. Each iteration or each run of this process somehow takes multiple days in order to enable us to see the result. So there is another simulator of this process that takes a couple of minutes in order to run with the same input and the same output. But the thing is, it is not very accurate, but it can provide us an approximation of the problem. So as a black box view, the input of the model is the biomass concentration, the pressure in Pascal, the mole fraction that are 3. So because we are going to have 3 different gas as the input, and the bubble diameter and flow in gas inlet. Whatever these fancy things meaning, so we can just look at them as some inputs. So we have here we have 7 or 8 inputs, and there is a black box that is doing something, and as the input we have a gas reaction rate for 3 gases. So we have 3 outputs, 7 inputs and 3 outputs. So we have 2 fidelities here, high fidelity one and low fidelity one. So in this graph we can compare the high and low fidelities. The dashed line is the ideal mixing or the low fidelity one, and the box plots are the high fidelity one. So we can see that they are somehow looks like each other, but still there are some differences that comes from the cost and time that we are going to spend in order to see the results. Okay, in terms of the describing the problem, we have a high fidelity one that we are going to label it as S equals to 1 with the cost of 7,200 of cost, and also we have a low fidelity one that we label it to S equals to 0 with the cost of 2. These 2 numbers are simply the amount of time that takes for each one in order to run, 2 minutes and 5 days. And we have 7 number of inputs, as I mentioned, and we have 3 number of outputs. So the MFBO process, in order to solve that problem, we use this paper that I mentioned here, multi-information source optimization, and the algorithm for solving this problem in a very simple form goes like this. We are using the samples that we already have in order to estimate the hyperparameters of the Gaussian process that we are going to fit to our model, and we have an amount of budget that we are going to use. So until this budget is not exhausted, we are going to determine what information source or fidelity we are going to use next, that is cost sensitive. So also the cost also is here. And also we are going to update the posterior distribution with the new observation, and we are going to iterate through this loop until our budget is exhausted. We have a couple of challenges here. One of them is, as I mentioned, the ratio of the high fidelity and low fidelity one is very large. So this will lead our model to use the low fidelity ones over and over and query those low fidelities instead of high fidelities. So this is a problem because it takes too many iterations for the model in order to be converged. So this is a challenge and somehow a problem of this scenario that we are facing. And as we see from this graph, if the ratio of the cost is very low, the number of queries from the low fidelity is a lot. So, and this is the problem. In order to implement the project, we use the next flow. And the reason for choosing this next flow in order to implement our problem is this project is not going to be used by us. We are going to give this problem to chemists in order to use it in their laboratory. So they are not developers, so they should have a user-friendly interface in order to work with that. So next flow is the answer. In a very simple form, the next flow does this. We have a Docker container that all the dependencies of our project is installed, mainly the blowtorch that the project is implemented based on that. And then all we are going to do is to just run the Python file that the high fidelity and low fidelity case is inside that. And as simple as this. And in order to provide this to the chemists, in order to use that, we use the next flow tower that they're going to just simply push the run button in order to run the project. So all the open source codes of this project and also the one-click run project of this code is available on the link that is provided here. And also there is one resulting paper of what I have discussed so far that is currently accepted in NeurIPS ComSost Workshop 2023, that also the paper is available on archive, so you can have access on that. Very thank you for Jacob for all the help and support, and also for Lars for being patient of very dummy questions from non-chemical guys. And thank you very much all. Thank you. And
all right, thank you, Mahdi. Yeah, I guess when are we gonna see the pipeline exactly, and how do you think people are gonna use it? I think obviously Lars is also on this project as well. So yeah. What do you have in mind for that?
In order to Lars and others to use the project, they can simply log into Matterhorn Studio and make their own project and choose the MFBO, provide their inputs, and click on the run and wait until the next point that we are going to recommend them. And then they can go to the laboratory, do the experiment, come back, add the number here, and wait for another iteration in order for getting a better result.
Okay, cool. Yeah. So that sounds really cool. And we'll get to that. All right. Thank you so much.
Thank you very much indeed. Thank you.